Okay, good afternoon. Let's start lecture. Okay, so we'll finish the threaded fastener and by looking at the tension joint safety analysis. Right. So in the previous lecture, we have derived the formulas for calculating the stiffness of the bolt, stiffness for the members. Right. So we're going to use the information here for analyzing tension joint safety. So the first topic is when you analyze the safety, basically we need to know the strengths, right? So in this particular case, we need to know the first topic is called bolt strengths. Okay, it's bolt strengths. So in terms of the bolt strengths, it's basically specified by this ASTM, okay, minimum quantity value here. So what that means is there are two concepts here. One is called proof load. Okay, so we're going to use FP at here. So let me draw this stress strain diagram. So a typical stress strain diagram so it will be looking something like that. Okay. And this is probably SUT somewhere here. Okay. And this is probably SY. Okay. So at right here, okay, this is basically, if you remember the stress strain diagram, there's a point called proportional limit point. So basically that's the limit, right, limiting point for this proportional straight line here. So this guy here is defined as SP. This SP is called the proof strengths. So SP is called proof strength. So SP basically is the limit of the proportional limit here. So generally, how you define that proportional limit, you can use that basically called 0.01%, right? The epsilon. The strain is when this is approximately 0.01%, and that's the location of this proof strength SP there. All right, yeah. So SP, okay, equal to a load divided by the area. So we're talking about the bolt, and bolt, when you talk about stress, basically if this is the stress at the threaded portion, so we use the so-called stress area, AT, right? Yeah, this AT value can be looked up from the table. So FP is what we call the proof load. So FP basically is the load corresponding to the SP value here. Okay, SP. So this is basically the two concepts here. Now, where do we find this SP value, the proof strength value, right? So this one, you can find them from a given table. A-9, A-10, and A-11. So A-9 give you this ASTM standard, SAE, and this is a metric. Okay, so the three tables are where you can find the bolt proof strengths. So we need to use this one later for the joint analysis. So given, let's say for example in the question, they're probably going to tell you, here's the bolt, maybe STM grade something, then you need to look at the table. So here's the table. I'll show you what the table is. Where is it? Yeah. So this is the table A-9, I believe. So there are different basically designations regarding this ASTM specification, right? For each designation, you have this so-called minimum proof strengths at this column here. Okay, so this is where you need. Okay? If you have a bolt given and you need SP, this is where you should look it up here, right? And if you're experienced mechanical engineer, sometimes you can tell by the markings on the bolt head and to know what grade that bolt is. Same thing for the SAE, right? Yeah. and SE grade number, minimum proof strength is here, okay. And metric, same thing, right? So they use a different sort of property class. And if I remember correctly, there was when I was looking at the table and then looking up on the internet, there was a little discrepancy somewhere here. In table, this is M16. If I remember that right, this is actually probably not 16 starting point. But anyway, so the metric ones, they generally put the grade numbers on stamped on the bolt head. Okay, so that's where you can look it up. Right. So basically, what the proof load is, it's the maximum load, right, for a bolt that can withstand without acquiring a permanent set, right? So this is the load. Okay, this is the maximum load. The bolt can endure without permanent set. Okay. Now, if you look at the table, you probably noticed the one thing here. So this column here, there's a keyword actually called a minimum. So it's always a minimum here, right? This is minimum. Basically, what that means is this is a statistic concept. So if you take a whole batch of the bolts here and then you test them, then you have this distribution at here, the histogram. So there is a minimum value here represent basically for that batch. This is 120 KSI, for example, right? So actually this is the number you're going to put that into the catalog, right? For this batch of the bolts, right, the proof load is going to be 120, not the mean value, okay? Not the mean value. Yeah, so why is that? Because this is basically a protection of yourself, right? Of the manufacturer itself. So when customer comes back, if you give the mean value, and there are some of them that's less than the mean value, so for sure there's some of them will fail, right? If you give the mean value as the value in the catalog. Okay. So that's proof load. Now, when we use the bolt, let's say we're trying to use the bolt on the tension joint. So the second concept is called preload. Okay, preload. So preload, this is a very important concept in terms of the bolted joints. Okay, particularly the tension joint. So what's the definition of preload? Okay. Yeah. So preload is generally a tensile load. Okay. Okay, it's a tensile load that the bolt is subjected to as it is stretched by tightening of a nut. Okay, tightening a nut. So you're using the bolt on the tension joints, or just maybe not necessarily tension, but you just clamp a certain number of members. So you crank the nut, okay, and tighten the nut until a certain kind of tightness, okay? And actually there has to be a certain standard to stick to. So while you tighten it, so imagine what happens, right? The bolt will be elongated, and the member will be what? Compressed, right? Will be compressed. So you actually need to elongate the bolt a little bit in order to apply this preload here. Okay, yeah. So that how tight, basically how tight you crank the nut here is determines how much preload you applied at this joint here, right? So that's the preload Fi here, right? So preload is a very important concept. The reason is, so let me bring up that picture here. The reason is, if we have a tension joint, the whole safety of the tension joint actually depends on how much preload you applied Okay. Say for example, this diagram here. Suppose that we have let's say we consider the bolted joint here as a kind of spring at here, right? So if you tighten that here, and as if you're kind of putting a spring, okay, you put a spring down here by 100-pound force. Okay, yeah. So once you apply the 100-pound of force here, then let's say you put a little sort of insert at here. So you let it go, and guess what? So basically, there's going to be 100-pound of force, right here, right? Basically, it's a clamping force of 100-pound force, right? So now, if I don't apply any external load, there's 100-pound force here. If I started to apply external load, okay, putting down, if your applied external force is less than 100 pounds, so that insert is not going to move, right? It's going to stay there as it is, basically. So that basically that means the joint is safe, right? The joint is safe. But only when what? Only when the external load is higher than this preload 100-pound force at here, then the insert basically will fall out. That makes sense, right? So this preload here basically determines how tight, the force is applied at the joint here. Okay? Yeah. Not necessarily saying, oh, you wanted to apply as much as preload Fi, right? You can't do that actually, because why? Proof load. So when you have a bolt here, you need to basically consider there is a proof load, which is what? The maximum load the bolt can take without permanent set. Okay? Yeah. So there are basically two folds that are here. You need to apply a proper preload, but at the same time you don't want to stress the bolt too much. Okay? So what should we apply the proper preload then? So there is this general guidelines here for the Fi value. Okay. It's 0.75 Fp if it is non-permanent joint. Okay. So non-permanent joint basically means you probably need to take off the cover or take off the joint to do some regular maintenance, right? That's non-permanent joint. But if it is a permanent joint, okay, then it's 0.90 Fp. Okay, yeah. So that's the general guidelines that we should use in terms of the Fi in here. Okay, so Fp is the proof load. So how do we get Fp then, right? And Fp basically equal to what? The At times Sp times the proof strength. Okay, so where do we get a Sp? Once you have the bolt, you have the Sp. So where do we get the At then? Once you get the size of the bolt, then you can get this At value, right? Depending on size. So that's where you can get the Fp value. Okay. Yeah. So then, now the question comes is, so if I have the bolt now, I have this, I now have knowledge of the joints, whether it's a permanent or non-permanent, and I can calculate Fi. So the question is, how do we apply this Fi properly, basically, right? Yeah. There are different ways of doing that. So basically, the question is, how do we relate the preload to tightening torque? Okay. So very common thing is you put your cars in the mechanics, and let's say change the tires or swap the winter tires with the regular season tires. So basically, every time when they tighten the lug nuts, right, they always need to apply a proper torque to it before they let it go. So how do we do that then? There are different different ways of doing it. one of the very mathematical way of doing it is, right, if when you apply the Fi, you know that what's going to happen is there's going to be a small deflection to the bot, right? Small deflection. So there's a little deflection delta which will happen to the bot, and mathematically this equal to Fi times L over AE, right? So mathematically. So basically what I'm saying is, well, you're trying to get exactly the Fi value. So if I somehow can measure the deflection caused by the Fi, so basically if I can measure this delta here, then I will have precisely how much Fi that has been applied to the bot here, right? So that's the nerdy way here. So, but this is a very unpractical, right? You know, measuring the deflection of a bot, that's basically too precise, right? And too complicated. So the second way is what you can do is you can use the so-called torque range. Okay. So when you use a torque range or pneumatic impact range, so basically you need to know how much torque you're going to apply it here. Now in the previous lecture, when we were learning mechanics of power school, we derived a formula for the load, for the torque, how much torque do we need to raise certain amount of a load. I wonder if you remember that, right? So you have the power school here, you have the load Fi, so how much torque we should apply to the nut in order to raise up the load, right, by considering all the external frictions into consideration. So in that particular case, we derived the formula. If you remember that formula is called TR equal to Fi dm over 2 L plus F pi dm second alpha. Yeah, you don't have to write this one here. I just want to illustrate the idea here. Second alpha, then plus Fi Fc dc over 2. Okay. Yeah. So what are these things here? You remember that Fi is a load, right? Basically, Fi is the amount of in this case, is the amount of the preload we want to apply, and dm is the so-called mean diameter, and alpha is the power school, and basically that's the in term power school it's 5 degree, and 29 degree I think. F is the friction coefficients. Okay, Fc is the friction coefficients of the collar. So there's a collar here, and there's the power screws, right? And then there's the nut. Okay, basically. Okay. So that's the formula for this one here. So for the DC value, okay, if we take the DC value basically as d plus 1.5 d over 2. So what's this one is basically, I don't have the drawing here. In our case, it's not a power screw. In our case, it's a bolt. Okay, it's a bolt, and under the bolt there is what? There is a washer surface, right? There's a washer surface here. So that washer surface, we consider that the washer surface which is in contact with a certain member here, okay, and that's basically the 1.5D, okay, and then plus this major diameter D there as the mean diameter for the DC over here. Okay, yeah, that's how you calculate. And then you the DM here, you can use the D. So replace all of this, and that formula can be simplified actually into kind of a simple formula here called K times Fi times D. Okay, so this torque TR, which relates to the preload, can be written as this KFI times D. So the key value here, the key value in general, the key value is approximately 0.2. If you don't know much of these other conditions or informations, you can take the key as 0.2. Otherwise, you can look at the table. You can also take a look at table A-15. Table A-15 give you some other definitions, some other conditions. for example, what's the bolt condition, whether it's a zinc plated, lubricated, non-plated, or cadmium plated, basically different bolt condition. Then the key takes a slightly different value from 0.2. Okay, yeah, but otherwise you can take 0.2 here, and that's how you can calculate this TR at here. Okay, so when you use a torque range, and that's what you can apply properly, approximately as a TR. Okay, yeah. So this is still a little bit mathematical at here. So in reality, there is some other technologies being used at here. They call it the DTI. Okay, so that's called the direct tension indicator. So this one here is pretty neat. So there, under here, there's a washer. There's a certain amount of silicone material at here. Okay, so when you put it there, and when you tighten the nut, and until those amount of the silicones squirted out here, and that basically indicates you applied the proper load here, right? So there has to be a match, right, for the application. Okay, so that's pretty convenient, of course. Okay, yeah. So that's how you can apply a proper load. Okay, yeah. That's good. Yeah. So now let's come to the tension joint here. Okay, let's come to the tension joint, and let's look at what can we do to analyze the tension joint. Okay, statically and also in terms of fatigue loading. Okay. So here's a tension joint. Okay, here's a tension joint. So for this particular tension joint, it's probably part of basically a pressure vessel, and there is some internal pressure P. Okay, trying to pull this tension joint apart. Of course, the bolt here is clamping it properly. Okay. So here's a whole bunch of definitions that we're going to need at here in terms of further application here. Okay, so I'll define Fi as we defined previously. It's called preload, of course. Okay. So this capital P at here is going to be this external tensile load. Okay. Yeah. So imagine what happens at here. If I don't have this external load P, and then you apply this preload Fi to it, so basically the bolt will feel a tension, okay, which is caused by the Fi, and the member will feel what? A compression, also by the Fi here, right? Also by the Fi. And now the external load capital P comes in the picture. Okay, come in the picture. So the external load comes in the picture, then part of the external load capital P is going to be taken by the member, and a part of that is going to be taken by the bolt. Okay, so taken by member and the bolt. Okay, yeah. So they're not completely taken by just one of the components at here. So now let's define this PB. Okay, let's define the PB as the portion of the P taken by the bolt. Okay, taken by the bolt here. Okay. And let's define this PM as a portion of the P taken by member. Okay. So imagine what happens next. If PB taken by the bolt, then PM is taken by the member. So how much of the resultant load on the bolt then? So let's call it FB. how much will be this resultant load on the bolt? Initially, the bolt feels a tension force Fi, right? Feels Fi. And now you have this PB coming from the pressure, inside the pressure, capital P, and then it's further being taken by the bolt. So FB should be equal to what? Fi plus this PB. Okay, so the tension force on the bolt is a little bit bigger now, okay, than the initial condition. Okay. So the Fm, let's see, if Fm is the resultant load on member, okay, resultant load on the member here. And what will be the resultant load on the member now? Originally, the member feels what kind of force? If there's no external load, the member feels Fi, which is compressive force, right? Compressive force we indicated as a negative value. So now Pm is the portion of P taken by the member. Pm is what kind of force? It's a tensile force. So basically the Fm, which is the resultant load on the member, that should equal to negative Fi plus Pm. Okay? So what you want is, you see what you want? You want Fm to be what? To be greater than 0 or less than 0. Fm is the resultant load on the member. Basically, here's a tension joint. If we're talking about safety of the joint here, the member actually have to always feel a force. What kind of force? Compressive. So really you want this one here, you want this one to be less than 0 here, right? Yeah. Okay, so let's define two more things that are here. So C, we define a C as a ratio. We call C is the fraction of external load carried by the bolt. So basically PB over PB plus PM. We define C as this. So PB is the portion load taken by bolt, PM is the portion load taken by member, PB plus PM is the total external force P. So this is C here, basically is called the ratio, okay, of external load P carried by a bolt, okay, carried by bolt. Then apparently 1 minus C, which is PM over PB plus PM. So that's going to be basically the fraction of the external load P carried by the member, right? So that's a C value here. In reality, maybe the gasket, not just one bolt, maybe you have n number of bolts. Okay. Okay, so that's all the information we need, and then let's derive some very simple mathematics that are here, okay, based on the information that are here. Okay, yeah. So before we move on here, okay, in general, when we analyze, we single out, basically just single out one bolt, okay, or one location for analysis here, right? Just for analysis. So when you single out one thing here, what you do is this capital P at here, right? This capital P here, okay. So that capital P maybe is basically equal to P total divided by the number of bolts. Okay. So you have the total, basically external force, then divided by the number of force, divided by the number of bolts. So that'll be the external load at one location, right? At one location here. Okay. So what I want to do next is I want to derive something first. Basically, right now the C value, the C is defined as PB over PB plus PM. I wanted to basically convert this one into the stiffness value for the member and the bolt. Remember we use Kb for the stiffness of the bolt and Km for the stiffness of the member, right? Yeah. So let's take a look at what's the connection between there. Okay. So imagine the situation here. You have this external load P, okay, applied at here. So how much of a deflection will caused by the PB, and how much deflection will caused by the PM? PM is applied to the member. PB is the force applied to the bolt, right? To the bolt. So PM will cause certain deflection, and PB will cause certain deflection. That makes sense, right? So PM, the deflection is caused on the where? On the member. And PB is the deflection caused on the bolt. And because they all at the same place, right? They all at the same place. So the deflection caused by these two, they should be equal to each other. Okay, should be equal to each other. Basically, the delta, if I see delta equal to this PB, okay, caused by the portion of the load on the bolt, so that divided by the stiffness KB, and that's deflection, right? That's deflection. At the same time, your deflection PM, okay, applied to the member, if you divide it by the member stiffness, and that causes the same amount of deflection delta there, right? Same amount of deflection delta. Okay, yeah. That makes sense, right? Because if they want to stretch, they have to stretch at the same amount of deflection, right? Because they are the same joint, right? They can't have the different deflection, basically. Okay. Yeah. So if this is the case here, we also have another situation, right? Another situation is with a P equal to PM plus PB. So three equations basically. So first, let these two equal to each other, right? Let equal to each other, and then we can derive PM equal to Km over PB over KB. Okay, or you write it as this PB like Km over KB. Okay, like this. Okay. At the same time, this PM equal to P minus PB. Okay, at the same time equal to this, right? So that gives us what? The capital P, actually that gives us capital PB equal, okay, KB over KB plus Km times P, right? Times P. Okay. So that gives us the PB value. So PB is proportional to the P, okay, by how much fraction? By the ratio of KB over KB plus Km. Okay. Yeah. And how do we define the C again? We define our C as PB over capital P. Okay, that's how we define the C value. So replace this one over here, so we get our C value as, okay, KB over KB plus Km. So the C, which is a fraction of the load taken by the bolt, okay, can also be written as the ratio between KB and the sum of KB plus Km. Okay, that's the C value. So 1 minus C, of course, is going to be Km over KB plus Km, right? Okay. Yeah. So then, if I go back just a slide get at here, my Fm. Let's look at this Fm at here, right? Look at this Fm. Fm equal to negative Fi plus Pm. So Fm equal to negative Fi plus Pm. So what's Pm then? Pm is the portion of the load taken by the member, and the C, okay, is defined as the fraction of the load taken by the bolt. So the Pm is actually just 1 minus C times P, okay, times P. Okay. So the Fm can be written as this value here, this function here, in terms of C, in terms of the P, and C is in terms of the stiffness of the bolt and stiffness of the member. So overall, what we want is we want this value to be kept at 0, less than 0, right? To be less than 0. Okay. Yeah. Okay. So if I draw a diagram at here, okay, if I draw a little diagram to illustrate what's happening at here, so this is basically what happens. Okay. So let's draw an axis at here. Okay. So let's say, suppose that the KB, this is the stiffness of the bolt. Okay, stiffness of the bolt. And Km, okay, this is the stiffness of the member. So basically, Km, the member stiffness in general, has a much higher stiffness than the bolt stiffness. Okay, so they are probably sometimes about 8 times bigger. Okay, 5 to 8 times bigger. So this is going to be the delta, and this is going to be the load F at here, right? So we consider them as a linear spring at here. So initially, without any external load, we have this Fi preload applied. So when we apply the preload, so let's say Fi is here. Okay, Fi is here. So which means you apply the Fi at here. So Fi will cause certain amount of a deflection, right? Certain amount of deflection. And same thing at here. Fi for the bolt, for the member, is considered as a compression. So same Fi. Okay, and that's going to cause another deflection in here. So let's say we call this is delta B, and we call this is negative delta N. So that's the deflection, right? Okay. So without any external load, right? Without any external load. So now you have the external load applied, the capital P, and the portion of that P is taken by the bolt, and the portion of the P is taken by the member, right? So how much taken by the bolt is PB value. So taken by the bolt, okay, which means where is that going to be? A little portion of the PB. So let's say maybe over here. Okay, so this portion, this little difference at here, okay, and that's PB, right? That's PB. So this guy here will be, the load will be what? Fi plus PB, okay, plus PB. Then there will be further elongations, okay, of the nut of the bolt, and this portion of this delta change, okay, that's the delta, right? That's the delta we rewritten at here. That's the delta PB over KB at here. Okay, PB over KB. At the same time, there's a portion of the load PM is going to be taken by the member. So what happens is portion of the load PM taken by the member, and for the member, the original compressive, PM is the tension. So basically you have a reduced value at here, compressive force. So now you're end up here. Oops. So now you at here now, right? You're at here, and this location corresponding to the deflection of this much now. Okay, what's the difference between these two then? The difference between these two is PM, exactly, right? Then the absolute value at here is going to be the negative Fi plus PM, okay, plus PM. And this portion of PM will cause, okay, a delta deflection. So this delta deflection should be the same as this much at here. Okay, this much. Okay. But overall, the effect of this external load PM basically for the bolt you have an elongated deflection, but for the member you have a reduced deflection at here, right? Originally it is here, and now it's here now. Okay, now it's here. So this is basically what happens before and after the load as an external load capital P is applied here. Okay, capital is a P point. So we can take a sort of a quantitative view at here as not a very strict here. Let's just say if this Km, okay, is approximately, let's say if I take a Pm as 8 kb, so the stiffness of the member, let's say, is about 8 times the kb. Okay. Now if Fi is initially 1,000 pound force, external load is 1,100 pound force at here. Okay, so let's see what happened when we have this capital P applied. Okay, what will be the resultant load on the bolt, and what will be the resultant load on the member? Just hypothetically value here, right? Yeah. So how do I calculate? First, we calculate the C value. Okay, we need the C value to do the calculation. So 8. So 1 plus 8 is 9. So that's 1 over 9. Okay. Yeah. So that means the portion of load which is going to be taken by the bolts is going to be 1 over 9 times P. So C times P. Okay, C times P. So 1 over 9 times P, that's approximately 122 pound force. Okay. Then FB, which is the resultant force, resultant load on the bolt, is going to be the PB plus Fi, and that's approximately 1,122 pound force. Okay. Yeah. Okay. And Fm is going to be 1 minus C capital P minus Fi, and that's negative 22.1 pound force. Okay, negative 22.1 pound force. So what does that mean? When you look at this value right here, what does that tell you? We still have a safe joint? Yes, right? So they are less than 0. But you look at this. If you look at this, the difference here. This is your original P here. This is a PB. So guess how much PM is? Is this value minus that value? That's actually almost 900, right? Almost 900. So basically, most of the external load is going to be taken by who? By the member, right? Going to be taken by the member, right? Yeah. Actually, that's what you want, because if you all the load taken by the bolts, then the bolt preload is already pretty close to the FP, right? The proof load. So it will easily be over the proof load if all taken by the bolt. Okay. Now, how do we basically manipulate then? How do we manipulate the situation in order to suit our needs at here? So let's consider this this situation here. Remember in the previous lecture, when we calculate the stiffness, we have one parameter called grip, right? Called a grip, and grip is indicated by the L. Okay, grip basically is the total if it's a body joint, basically that's the total length of all the members being clamped together, right? The total length. Okay. So what's the connection between the grip L and the KB? So there's a connection here, actually. Longer grip, okay, and your smaller KB. Okay, you have a smaller stiffness okay, KB at here. Okay. If it's a smaller KB, then let me just sort of my mind here. If it's a smaller KB, how does that affect the C value? C value is KB over KB plus KM. So that means what? That means this, right? So smaller KB means the C will be smaller, will be bigger, right? No. Oh, yeah, it will be smaller too, right? Sorry. That make sense? Yeah. Smaller C value, meaning, what does that mean? So how much load being taken by the member? It's 1 minus C multiplied by capital P. So smaller C value means there's going to be more load taken by the member. Okay, yeah. There's a little, basically, some intuitive things that here you can manipulate, right? Okay. All right. So now let's make use of the information here to do some analysis here. Okay. Yeah. Now we analyze the safety of the joint. So first, let's look at the static situation. Okay, static. If it's a static one, okay, what we need to know is we need to calculate basically the stress, okay, on the board. So first calculate the tensile stress on board. Okay. So let's say we use a sigma B to indicate the tensile stress on the board. Stress is connected to the load on the board. And the load, in our case, we use FB, which is a basically resultant load on the board, right? Resultant load on the board. So we divide it by the stress area, AT. Okay, that's from the table. And FB, if you look at the formula for the FB, which is the PB plus FI. Okay, and PB, I'll just write it down here. So PB plus Fi over AT. And PB is what? If I use the C value, PB is equal to C times capital P, right? C times capital P. So your sigma B value, okay, is Cp plus Fi over At. That's the tensile stress on the board, right? Tensile stress on the board. Okay. You're comparing the stress with the strength. So in this particular case, what's the strength for the board? It's that what? The proof strength, SP, right? SP. Okay. So this is the first kind of basically safety analysis. This is what we call the yielding factor of safety. So now I have this so-called yielding factor of safety. So we define that as NP equal, okay, SP over, okay, sigma B. Okay. Yeah. So SP divided by this guy here, so that gives us SP and AT over CP plus FI. Okay. Okay, so that's the safety factor guarding against the bolt yielding. Okay. And it's pretty common that you load the bolt very close to the proof load, okay, to the proof strength. So this value AP in general will be very, very close to 1. Okay, so maybe 1.0 something, so that's okay, right? Yeah. So this is going to be close to 1. Okay. close to 1 and greater than 1, right? Yeah, so greater than 1 and close to 1. All right, so that's the yielding factor safety. Now the other way, the other format of analyze the safety is, so what people do is they apply so-called load factor. You see this capital P here, right? Capital P here is the external load. So they apply a safety factor directly to the external load, capital P. So basically, they use a safety factor NL at here for this safety factor, capital P. So what that means is, so this is basically the first kind of a calculating safety factor, and the second kind of safety factor is called the load factor. Okay, load factor. So the load factor is applied like this. So you call that C. This is called NL. CNL times capital P, okay, divided by AT plus FI divided by AT and equal to SP. So this is another way of analyzing the joint here. Okay, so you're basically putting the weighting on the load, capital P. Okay, so the original formula is just kind of slightly modified here. Okay, so that derive the NL should be equal to capital SP AT minus FI over C capital P. Okay, yeah, so that's the other way of it. You need this one to be greater than 1, of course. Okay. Okay. Then here there's another one. The third kind of analysis for the joint safety, and we actually said that, which is what we wanted to keep. Which value? We want to keep this Fm value to be less than 0, right? Less than 0, because if it's greater than 0, that means the two members. If there are two members being clamped, that means the two members will be separating from each other, right? So keep Fm less than 0. That's the third kind here. Okay. So let's just suppose that we let this here. This is Fm, right? So we call P naught is a particular value at which your Fm is 0. Okay, your Fm is 0. So we can calculate what is basically the external force or external load P naught, okay, that caused the separation. So this is the critical external load. So that means the P naught equal to how much? Fi over 1 minus C, right? Fi over 1 minus C here. Okay, that's P naught. Then the safety factor N naught is what we define safety factor guarding against separation. So this is the safety factor against separation. Okay, this is safety factor in separation. So P naught is the critical load value. So we use the P naught divided by the current P, and that's the safety factor. Okay, yeah. And you want this one to be greater than 1 to be safe, right? Okay. So basically 3 different safety factors, okay, for this particular tension joint. Okay, a question could ask is, what's this safety factor, what's the other safety factor, and what's the other safety factor? Okay, so technically you need to calculate all 3 safety factors. Okay, so let's take a look example. Any questions? All good? Yeah. So let's take this example is sort of a extension from our previous example. Okay. Let me bring up the picture here. It's not working.
which of these safety factors would be the one you should concern yourself with more?
Hard to say. I think you need to check basic law. The first and the second, the first and the last one, the first and third one.
Okay.
Yeah. Not this lecture. Yeah, so let's take a look at this guy here. That's very much similar to what we did in the previous lecture. Previous lecture we derived the safety factor, they derived the stiffness for the bolt and the member here, right? So now let's look at overall coming to the joint safety here. All right, so there are some dimensions here. So A is 100. They're all in millimeter, I guess. Yeah. So D and E are the same value. So D equal to 20, E equal to 20, and the B. So actually, we don't really need the B value. B equal to 200, C 300. Okay, so that's sort of pressure vessel at here. Okay, yeah. Effective sealing diameter. This is what we need. Effective sealing diameter equal to 150 millimeter. The layer D, the member D is second here. This is steel. So layer the D is steel, and the E is iron. Okay. So in your, this is actually probably one of Simon's questions. So I just kind of taking out of the Simon question here. So I'm not gonna calculate all the details here, but let's just look at roughly the bigger picture here. Okay. Okay. The bolt, what we used here is ISO class 5.8 bolts, okay, with a diameter of 12 millimeter. So basically it's like M12 times something, right? Yeah. We have, how many bolts do you have? We have 10 bolts. So 10 bolts at here. Okay. And I wanted to, their pressure, yeah. And pressure, capital P. So basically this is the P total, right? The total pressure in the vessel is 6 megapascal. Okay, 6 megapascal. So we wanted to calculate the load factor and a separation factor in knot, just for illustration. Okay. Okay. So what do we need first? First, we need to do is we need to obtain the capital P basically on one individual joint. Okay, bolt. So capital P. So we need to use this information in here. So the effective sealing diameter. Okay, effective sealing diameter. Some of the diameters, this A, B, C, they actually it's not necessary. If they're giving there, they're just trying to confuse you. So effective sealing diameter, that gives us the effective area, sealing area, A equal to pi d squared over 4. Okay, so that's 150 there. Okay, so that's how you calculate the effective area here. Okay, yeah. And then we have the total pressure, inside pressure is 6 megapascal. So then that means the load, okay, the load on the sealing, right, on the sealing is going to be, so the load, okay, is going to be 6 times the area, right, 6 times area. Okay, so 6 times area. So this is already millimeter, and the megapi is a millimeter square. So that's okay. So basically the millimeter cancel out each other, right? Yeah. And the unit coming out of here should be what? Should be Newton, right? Should be Newton. So then I'll times 10 to the power -3 to change that to kilonewton. Okay, yeah. So that's the total external load. Okay, so total external load, we have a 10 number of bolts. So at the 1 bolt location, the load capital P is what? 1/10 times, okay, this value, right? Times this, and that gives us approximately 10.6 kilonewton. Okay, yeah. So this is the capital P we're going to use for our calculation. Okay, for our calculation. Okay. To do the calculation, we have to go through actually quite a bit of steps here. First, we need to calculate the bolt stiffness. Okay, the bolt stiffness. So this is actually, this part of the question is you need to look at all different kind of tables here, right? Remember in the previous lecture, when we calculate bolt stiffness, we have to calculate what? The threaded portion and unthreaded portion inside the member, right? By going over table A-7. Yeah. Okay, table A-7 is for calculating the bolt stiffness. Okay, so I'm not going to go over that section now. So the key information is the diameter, okay, the D here, okay. Yeah. So let's say in my particular case, I obtained my K1, I obtained my bolt stiffness KB. Okay, the value of the KD is ADATE over ADLT and ATLD, right? That's the formula. So you need to find LTLD. ADAT, they can easily be found. Okay, so that's gonna be approximately 539 meganewton per meter. Okay, meganewton per meter. That's gonna be the KB value. So do exercise. Okay, the way of the process of finding KB. Same thing for the member stiffness. So basically exercise how to use this table A-7 properly. Alright? Yeah. And you also, you got to be careful, because you see this kind of question, the danger is if you got let's say you got LT wrong, basically the rest of the calculation is all going to be wrong, right? So just one calculation wrong and somewhere at the beginning, and right? Yeah. So member stiffness, that's going to be the previous lecture. So look at the pressure cone, right? And look at how many frustum inside this pressure cone. And look at the geometry. You have the general formula for calculating the stiffness for each pressure, each frustum, right? Then take all the frustum as springs connected in series. Then you can calculate the total stiffness of all the members, right? So in this case, we have only 2 members here. Okay, 2 members. In this case, 2 members, same thickness but different material, right? One is steel, one is iron. So basically, you need to just apply the formula twice, right? Just apply the formula twice. Okay. So now I'll just assume I have calculated that. Okay, I'll just assume I calculated already. So 2 stiffness in series, and let's see, I got this value here. Okay, so bolt stiffness and the member stiffness. Then the C value, as we defined, is KB over KB plus KM, and this is approximately 0.27. Okay, 0.27 here. Right? Yeah. Okay, so now we're ready to calculate the safety factor. Calculate safety factor here. So to calculate safety factor, we need the proof strength SP. Proof strength SP. So what's the bolts here? This ISO 5.8 class. Okay, 5.8 class. So now let's look at the table that I showed you, which is the table H811. A-11 here. Let's see what do we have for that table, from that table. Where do you go? Right here. Okay, so 5.8. I don't have a 5.8 here. Oh, you're right. That's right. Metric. Yeah. So 5.8. So the SP is 380 megapop, right? 380 megapop. Okay. Okay. So this is table A-11. A-11. Okay. So this is the pressure vessel. Generally, it's going to be a non-permanent joint. Okay. So non-permanent joint. If it's a non-permanent joint, that means the Fi is going to be how much? We use 0.75 times the Fp, right? Times the proof load. And proof load is related to At times the proof strength. Okay, times proof strength. At is the stress area. So stress area in this case. Let me see, do I calculate here? Let me calculate here. Yeah. Stress area, what's the baud here? The baud is 12 millimeter here, right? The meter diameter 12 millimeters. So I don't have a table here. Yeah, I have a table here. So the in the previous handouts, you have a table here. We're looking at metric series 12. Yeah. So 12. And the course series is 84.3 millimeter square. Okay, 84.3 millimeter square. So that's table A-1. Okay, A-1. So AT equal to 84.3 millimeters square. Okay. So for just one question, you're flipping through the text for at least 10 tables in order to solve all the different, get all the different values here, right? So that gives us Fi 24 kilonewton. Okay. That's it. That's all the numbers you have now. Then all we need to do is to substitute all the numbers into the safety factor equation. So in this case, I'm trying to calculate this guy here and trying to get this guy here. So what do we have here? So NL equal to SPAT minus Fi over Cp, and that equal to 2.89. So all the numbers that we already calculated. Okay, yeah. And N naught, okay, equal to P naught over capital P, and P naught is Fi over 1 minus C. Okay, so that's N naught formula. So this value can be approximately 3.10. Okay, so those are good, right? Those are good. Okay, yeah. All right. So you see the process here now? Yeah, the flow of the logic here, right? Yeah. So tension joint, body tension joints, and as I said in the previous lecture, okay, it's 100% guaranteed. I will test you, okay, basically to what extent. Maybe it's going to be a complete question like this, right? You look at the assignments, basically that's kind of from the member stiffness, basically from member stiffness, ball stiffness, and up to the joint safety factor, right? Maybe this category, maybe the other one, but okay, know where to find all the values from the table. Okay, any questions? All good? Yeah, so just a quick basically on fatigue loading. Okay, we're not gonna test this in the exam, but just sort of an introduction as how do we deal with the fatigue loading on the tension joint in here. Okay, fatigue loading. So the starting point basically is from the resulting load, okay, FB on the bolt, and that's CP plus Fi, right? So that formula, CP plus Fi. So what do we mean by fatigue loading at here? So that means basically that external load capital P at here is not a static value, it's a varying, fluctuating value. So the P probably changes from P mean up to P max, right? So that's basically the fatigue part. If this is the case, then the resultant load on the bolt not going to be constant either, right? And so the FB has a certain mean value corresponding to the P mean, and FB has a max value corresponding to the P max. Okay, yeah. So that's the fatigue part. FB cause a stress on the bolt. If it's not constant, then what do we need to know? We need to basically, just like fatigue loading, what do we need to know? We need to know what's the alternating component and what's the mean component, right? What's the mean component? And an alternating component equal to what? Equal to the max minus mean over 2. And mean component is a max plus mean over 2. Right? And what gave us a sigma max then? Sigma max gave this yield sigma max. What gave us a sigma mean? And this yield sigma mean. Right? This yield sigma mean. So that's how you can get the alternating component and the mean component, because ultimately you have to apply those modified Goodman or Soderberg line, you know, a different criteria, right? Yeah. So basically, if you use F max here divided by AT, so that gives you max, right? Yeah. So that can get sigma A and a sigma M. Okay, sigma A and sigma M. Okay. So once we obtain the sigma A and a sigma M now, okay, and we basically need, what we need to do is we need to look at, okay, how do we design, or how do we analyze the situation here. So let's say I'm gonna use modified Goodman for the analysis set here. Okay, modified Goodman. So modified Goodman is what? This is SUT and this is SE. Okay, that's modified Goodman. Okay. So now, for our situation at here, and what we have is, okay, we have initially, what's the load? It's this, right? If there's no external load, capital P, your initial load is Fi. Basically means what? Which basically means your sigma M value, okay, your sigma M value is not 0, right? Initially, the sigma M value actually it's because Fi at here, right? Because Fi. So the pair of sigma A and a sigma M, which is basically the state of stress, it starts from 0, and then there's Fi over At, right? That's basically this case here. So where does it start? Maybe it starts here. This is the point here. Okay, this is the point. Okay. Now, if you recall that in the fatigue loading analysis, so in that lecture we did is, okay, here's the state of stress, right? Here's the state of stress. So how do we get the safety factor? So what do? We can basically draw a line, okay, which is what we call the load line, right? A load line here. And this line will intersect this criteria. Let's say this is modified Goodman. And this is the state of stress. Let's say this is A point, this is B point, right? What's the safety factor? Safety factor basically it's this portion divided by this portion, right? By this portion. But the problem here is, okay, in that particular case, yes, it's possible we can start from 0, 0, right, for the state of stress. But for this bolt here, it doesn't really start here. It's actually starting here. So what you do is you you draw the load line, okay, like this. Okay, you draw the load line like this, and the slope at here you're taking as sigma A over sigma m. Okay, sigma over sigma m. So if you have a safety factor somewhere here, if you have a state of stress over here, then safety factor will be this distance divided by this distance here. All right? Yeah. So anyhow, as I said, I'm not going to test you in exam. So basically, the whole point here is, you know, it's the idea is the same thing as fatigue loading. Okay, in the previous lecture, it's just the initial starting point is a little bit different. Okay, from the lecture 6 or something, right? Yeah. But other than that, the way to calculate safety factors is still the same thing. All right? Yeah. Was that good? Okay. So just focus on the static loading part. Okay. Focus on how to use all the tables properly. Okay. All right. Good.